This is lecture 22 for combinational circuit design. So before starting today's talk, first review our previous lecture. Our previous lecture was lecture 21, and that was devoted to SPICE MOSFET models. Here we have a typo, models. And first we consider level 1. So level 1 model, its ID expression was quite similar to the one we have studied in this course. So the only difference was we have additionally considered lambda times VDS dependence. So that was all for level 1. And after that we have seen that level 3 model, we have more complicated empirical expressions for IV characteristics. After that, we considered the standard model called BSIM, and BSIM has many different family members in it. But nowadays, since the FinFET and gate-all-around transistors are mainly used in our VLSI, so the one called as BSIM CMG is the standard model of our use. So one particular feature we have to understand for this BSIM is its capability to consider arbitrary cross-section. So simply means that if we have a certain FinFET like this and covered by the gate in this way, then how can we consider the IV characteristics of this FinFET, or in that sense, how can we calculate the electron charge density as a function of gate voltage? That is quite a big problem, and previously people introduced many different models for different cross sections, but fortunately for this BSIM CMG, so we have introduced a so-called unified model or universal model, and that is corresponding to these two quantities, like some length of this perimeter, so underneath the gate, so that is one thing, perimeter, and another one is the area of our transistor, so silicon reason, so we have area. Only with these two quantities it is found that more or less the inversion charge density as a function of gate voltage can be expressed in a single expression. So that is really huge discovery. So BSIM CMG adopted this kind of observation. And at the end of our previous lecture, I introduced a future direction of compact modeling development. So that is neural compact modeling. So inside this BSIM CMG, we have almost 1500 parameters. So with these parameters, actually you can match almost everything. But you know, it takes quite a long time, and calibration is really a painful procedure. So instead of that, the technique is just to get a lot of data from the experiment, then our neural network try to mimic the experimental data. After that, if we change slightly gate length or gate width, then its dependence is well described by this neural compact model that is regarded as a future direction, but I'm not quite sure whether that will be realized in practice or not, because sometimes or in many cases the accuracy of BSIM model or any kind of MOSFET compact models are really high. So that was the review of our previous lecture. So now we wanted to move to the chapter 9. So chapter 9 is devoted to the combinational circuit design, and I think that we will spend 2 lecture hours on this chapter. So today's lecture is devoted to the CMOS static CMOS circuit, and the later one will be devoted to non-conventional circuits without using the static CMOS. So let's go to this introductory part. So in this introductory part, we just make a distinction between the combinational circuit and sequential circuit. Sequential circuit will be discussed in chapter 10, and I hope that will be covered in our lecture 24, second last lecture of our entire semester. Combinational circuit, it is the circuit we have studied up to now. Its output depends only on the present input. For example, let's say inverter. If you have A and if you have Y as an output, then previously you had something, for example 0, 0, 1 and 1, 1, 0. Let's say that your input has changed in this history. Yes, then what will be your present output? Your output will be just 0. And let's say that you have just to keep the value as 1, 1, 1, 1. What will be your answer? It will be again 0. Whether you have previously some values like 0, 0, or 1, 1 doesn't make any difference when you have the present output value. Your output is always dependent on the present value of your input variables. That is quite easy to understand. So now let's go to sequential circuit. It has memory. So therefore, although its input is 1, current input is 1, but depending on its history, so it can have different behavior. So that will be covered in our lecture 24. So for while in this lecture and next lecture, we will keep just considering combinational circuit again. And now, as much as the combinational circuit is involved, then how can we implement this circuit category? So the basic way is static CMOS. So they use CMOS, so try to drive 0 and 1 output respectively. So this is the one we have studied up to now, so nothing new. And it is robust and fast and energy efficient and easy to design. So it has many good properties. So actually I want to say that for general purpose, this static CMOS circuit is the one we have to choose. However, for some special cases, we can have unconventional or non-static CMOS type implementation, and they are called as layered circuit, dynamic circuit, and fast transit circuits. So that will be covered in our next lecture, lecture 23, I hope. So I will try to anyway finish our discussion in one session. Okay, so today we will consider the static CMOS gate. But then static CMOS gate, about it we have already studied quite a long time. So what is the remaining thing? So we will just consider some uncovered topics in this CMOS gate. And I think that this is the final slide for introductory part. And let's review our previous discussion on the propagation delay. Propagation delay is simply proportional to these factors. For example, if we have a large capacitance, then it takes some time to charge and discharge. And the amount of charge is not solely determined by this capacitance, but capacitance multiplied by this delta V, actually it is corresponding to our VDD. So that is corresponding to the amount of charge we have to charge and discharge. So we have C times V as an amount of charge to be charged or discharged. And our capability to charge and discharge for this capacitor is simply given by the driving force. So usually this I is the ion of our transistor. Okay, so therefore if we wanted to minimize this time delay, propagation delay, then what we can do is, of course, reduce capacitor, reduce voltage, and increase current. So everybody can understand this kind of instruction quite easily. So of course, if you wanted to reduce the capacitance, then what is the problem? If you wanted to reduce capacitance, then you are introducing the smaller size of your transistors. So that is corresponding to actually the reduced capability to drive a certain amount of current. So they are closely related. So that's the reason why we cannot make the smallest capacitance because that is always related with reduced current. Also, how about the reducing the voltage? So that is actually we wanted to do every time. So we wanted to have a small VDD value. But if we reduce a small VDD value, then that will also introduce some problems. What is the some problem? Because our MOSFET and PMOSFET has, unfortunately, the so-called subthreshold slope, which is even for nowadays close to 60 millivolt per decade. So if we wanted to, for example, keep the ratio like on current and off current larger than, for example, 10 to the 5, it means that even for our best device, we need at least 300 millivolt to get this kind of separation between on current and off current. And you know that this 10 to the 5 is not that much difficult or too overemphasized value. This is just a conventional value for our high performance one. Our low power device need even further one. So therefore, I think that at least we have to have some margin beyond 300 millivolt, so that reduce the further reduction of our VDD. So VDD cannot be reduced any further, and even for nowadays, VDD value, when I was in company, so working in company, so that VDD value was at the time newly set to be 0.7, and more than 10 years have passed. And what is the VDD value of a state-of-the-art device? That is still 0.7. Sometimes we can find some literatures having 0.65, but anyway, we have no further reduction of VDD value significantly because our transistor has certain requirement or certain separation between its zero value and on value, because it has limited some maximum value of subthreshold slope. Okay, everybody can understand this one. Anyway, we want to given since this course is intended for designers, so we are not trying to change technology. Given technology, what can you do? So we wanted to do something. So especially in the second lecture, not this lecture, we will consider so MMOS only techniques, because yes, so MMOS has usually higher mobility and it is faster. So if we wanted to use fast circuit, high speed circuit, then usually we wanted to increase the current, and NMOS is much more preferred than PMOS. Okay, so we wanted to do it in the next lecture, and today's lecture is just devoted to some additional topics about so static CMOS one. So our discussions start from an example of a multiplexer. So now we have three signals. Of course, we assume that signal S, this is a S and S bar, both of them are allowed. And let's say that we wanted to have this multiplexer operation. So simply speaking, when S equals 0, so select 0, then Y becomes D0. So if we have S equal to 1, then Y becomes D1. So multiplexer just select our input argument between D0 and D1 is select, and Y becomes the selected one. So in general, we have something like this: D0 times something, or D1 and something. So let's express it as this form. So here we have D0 S bar and D1 S. Yes, it can be written as this form. Anyway, if we just draw the logic diagram, then we will draw in this way. Okay, this is AND for this AND operation, and this is another AND. So then after that we just take OR operation. But now everybody understand that actually AND and OR, these logic gates are not readily available to us, because we, instead of that, we wanted to have NAND and NOR. So how can we change this desired operation into, or using the NAND and NOR gate? So that is a simple question. And here, for that purpose, we use De Morgan's law. So simply speaking, it means that taking the inverse of AB becomes inverse A or inverse B. So I'm just writing down this one, and the other one is inverse of A or B is simply given by AND of A bar and B bar. So that is just given as this diagram. So when we have, for example, this is NOR, and this is NAND, and this is NAND, and it can be equally expressed as this form. This is OR, and before taking the OR, we take the NOT and NOT. So you can understand this NOT is corresponding to this A bar, and this NOT is corresponding to this B bar, and taking the OR corresponding to this one. So although we are much familiar with drawing our NAND gate as this form, but this is another equivalent form of NAND. So same happens for our NOR. So although this is NOR, however, this can be regarded as also NOR gate. Okay, so this kind of drawing is called as a bubble pushing. So simply speaking, if you push this bubble from the output to the input, then please just to exchange or swap the form of your logic gate. Previously it was AND and it now becomes OR. So okay, so now our goal is, now we have a AB plus CD, AB or CD, and we wanted to change it to different forms. So using the bubble pushing. So starting from this original form, we can just add, for example, here bubbles. Here in the B, we just added bubbles. Then these bubbles means that here we have a not and not twice. So this is just to become a buffer and identity. So we have nothing here, and we have nothing, and we have nothing here. After that, now you can understand this is here from B to C. Actually, this is not, and this can be just represented as this bubble. Yes. And also we have here bubble and bubble. These 2 times bubble is just cancelled out. Then finally we can have this form, the B, oh it's not B but D. So this is an AND and this is an AND. We know it. And you know, although it is written a little bit different form, but this is also NAND. So you know it. So by using this bubble pushing, we can make this kind of a transformation, and this kind of transformation is well supported by this expression. So for example, yes, now you can say that this is true. So first of all, we take the NAND over AB and takes NAND over CD and take once again the NAND. Then that is corresponding to this F value. Okay. So now let's go to the other ones. Our example is AB or CD, and if we use just NAND gates, then we can make it in this way. So use 3 different NAND, so we can make it. And let's try to count the number of our transistors. How many transistors are used in this D implementation? In this D implementation, we will spend 4 transistors for this one NAND, and another 4 transistors will be consumed, and also another 4 transistors will be used. So in total we will spend 12 transistors for implement this single operation. And now let's go to the compound gate. Please recall our lecture 2. We have already covered it. Without dividing it into small pieces, we just make one stage for our logic operation. So how can we do that? So that is simply given by this form. Okay. So then now you can see that. Then let's try to number of transistors. 1, 2, 3, 4, 5, 6, 7, 8. After that, here we have one more inverter, so we have two transistors, so overall we can have 10 transistors. Wow. So compared with our previous one, like this combination of three NAND gates, we can reduce the use of transistors. Yes, that is a quite significant reduction. However, it does not, I mean that from the viewpoint of our area, it is certainly beneficial. Then how about in terms of, for example, delay? So what happens? So you can make a comparison between your two design. So please, in this slide is taken from our textbook, and there is a misspelled one. So here, please regard this box, this broken box, as a dot. Then you can find that actually, from the viewpoint of a delay, it is not that easy to say. So sometimes even seemingly it is, for example, seemingly since we have a lesser number of transistors, so maybe it is also beneficial in terms of delay, but in reality it cannot be so in some cases. Please check this one in your textbook. And another topic here is input order. Yes. So what is it? This figure 9.6 just to show you on inverter. Oh, sorry about that. Non-NAND gate A and B. So if I ask you, is A is faster or B is faster, then up to now our answer will be their propagation delay is the same because they are symmetry, and A signal, B signal has the same amount of delay. However, let's have a look at this real implementation. Maybe we have discussed this topic in our previous discussion on the logical effort. And here we have so-called inner input and so-called outer input. So inner one is close to the output, and outer one is close to this power rail. Power rail means that ground or VDD. So in this case, in logical sense, A and B should be balanced and symmetric. However, in its real implementation, in PMOS path, they have the same path. But unfortunately, in the case of this pull-down network, we have anyhow certain order, A and B. One is close to the output node, and one is close to the power line. So let's try to estimate the Elmo delay. Sorry about that. This is stuck once again. So let's wait for a while. Okay, so now let's say this way. In this scenario, we are assuming that it has two inputs. However, one input holds a stable one. So previously, for example, in this case, let's say that A is always 1. Oh, sorry. Not this one. This is just a logical number. 1. And previously B was 0. And at a certain time instance it suddenly becomes 1, then what will happen? Now B is turned on and we have the connected loop toward ground, and Y will be discharged and down to logical 0. That is expected. Or consider the opposite case, like instead of A, let's say that B is always kept as 1. However, A was previously 0 and now it becomes 1. Then what will happen to this guy? This is our two different situations. I wanted to say that if everything is ideal, they should have the same response. However, in reality, inside our NAND gate, anyhow we have to make some inner input and outer input, so they will behave differently. So let's have a look at it. For example, let's consider the first this case. In this case, input B lies later. A is already arrived as a 1 and stayed there. Then what will happen? So now we think that this is logical 1 because this pull down network is just disconnected, and A transistor is logical 1, but you know this B is 0, so current should be 0. Then what will be the value of this node? The value of this node will be simply given by VDD minus threshold voltage of our N MOSFET. Okay, so are you with me? In this case, the transistor is turned off just at the because the voltage is gate to source voltage is just threshold voltage, so we cannot increase it any further. So this is the case. Okay, so although this is not exactly 0, of course, because we have a certain margin, but it means that still we have some differences between our node voltage here and this one. So what will be the Elmo delay? So from the viewpoint of this one, then now we can say that Y port, and here we have another port which is another node biased in this way, and here we have R, and its R value can be regarded as just half of standard R. So usually please note that this R is the resistance, equivalent resistance of unit with N MOSFET. So since we are talking about N MOSFET, there is no penalty about mobility. However, since our transistors are twice wider than the unit one, so our resistance is given by this way. And here we have capacitance like 2C, and here we have a capacitance 6C. Of course, this 6C is originated from our P MOSFET, and N MOSFET. That is situation, and here we have also different half R here. Then we wanted to consider the discharging time for this Y node. And you know that here we have also the discharging phase for this first line. So this path also should be discharged. This one is discharged, and also this one should be discharged. So simply speaking, in this case, our simple rule to calculate the Elmo delay just gives us half R times 2C to discharge this first capacitance 2C, and another one is to half R and half R twice, so R times 6C. So it will give us 7RC as a estimated Elmo delay. Hmm. Yes, so this is not that difficult to understand, but what is the point? The point is now consider the opposite case, like A rises later. So in this case, B is 1, then please try to estimate the value of this node once again. Now, A is 0 and B is 1. So, if we allow any value of this node, X node, which is larger than 0, the double precision number 0, then that will conduct certain current. However, this serially connected A and B transistor MOSFET should not conduct any current. So simply speaking, it is certain that this X node should be fully discharged. So the value of our node here is really X or really 0. It means that, okay, here we have ground. However, at this case, this node is already discharged as 0. So we don't have to consider the discharging time for this 2C because this 2C is already fully discharged. Then the remaining thing is only this one. Okay, so actually we have to consider this one. So since here we have the real ground, this is just the intermediate one. So we don't have to discharge this 2C, but we have to discharge this Y node. And simply speaking, the Elmo delay will be R times 6C. So 6RC will be the Elmo delay. Then what is the meaning of this simple calculation? Although in NAND, A and B should perform equally, however, in reality, due to the order of their input, they can have different Elmo delay. So what we can say is, if we know as a designer, if we know that one particular signal is known to arrive later than the others, then it is beneficial to connect it to this A node instead of this B node, because the system just consider the overall propagation delay. Although, so the output Y here, the output Y is obtained by the combination of our A and B. So, although one is well established already, however, total propagation delay is simply given by this later coming signal. So, it is better to assign this faster path or faster input to the late signal. So that is the thing we can think. So which one is beneficial? So certainly this A is more preferred one for faster transition. Okay, so-called inner input. Then now let's think about this one. I think that this is well understood once we understand the asymmetry between our two inputs. For example, let's say that we wanted to have this case. Here we have A and B. However, once we have reset equal to 0, then this NAND is just working as an inverter. So now we have Y equal to A. This is just a buffer. We wanted to send our A into Y. However, if we have reset equal to 1, then this one reset bar becomes 0. So we do not send our signal to the Y. So in usual use case, in many cases, reset is just given as what? Given as just 0. So we just use, in many cases, use this system as a buffer. However, for special cases, for some special occasions, we wanted to turn it off. So I wanted to say that A is really frequently changing and it is important. However, in many cases, this reset can be just regarded as not reset bar. Reset can be regarded as 0, and we can slowly turn on this reset and slowly turn off this reset. This is quite a rare case operation. Okay, then if we suppose that A is most critical in terms of speed and turning on reset or turning off reset, that is not that important, then our obvious choice is A is assigned to what? Assigned to inner part, and yes, reset is assigned to the outer part, outer input. So that is the thing we can think easily. So 2, 2. This is the reasonable way to do that. But in this slide, we have further consideration. Okay, now we understand if we just take this kind of operation. So here, let's say that we just have the conventional design or the ratio, and MOSFET ratio. Then we have A here 2, and for reset bar we have also 2, but still we have a shorter delay time for A. Yes, however, if we further emphasize only A transition, then by sacrificing the propagation delay of our reset, we can even further reduce the propagation delay of our A parameter. Please note that usually reset is just given as 0, so it reset bar, this one becomes 1. So in this one, here we have quite strange ratio like 4/3 and 4, but this is intentionally made because that will give us something like in terms of our unit transistor resistance, we have 3/4 of unit 1, and here we have 1/4 of unit R. So by serially connecting them, then we still have equivalent resistance. So okay, good. But point is, now once we have this kind of behavior, now our reset transistor is turned on and it has something. So now when we consider the capacitance seen from this A node can be reduced significantly. For example, starting from A, then which one is seen? So you can see that 2 times wider P MOSFET and 4/3 times wider N MOSFET. So by summing them all, you will have 10 third. Okay, so what was the usual value? It was 2, 2. So input capacitance was just 4 compared with this 4. You can see that this one has no much lower input capacitance. So input capacitance really determines the propagation delay, so it is quite beneficial. Let's consider an extreme case instead of this one. Okay, here we have 2 to 4, but what happens if we have, for example, 100? Wow, then what will happen? What is the value of this n to get the real R value? So the equivalent resistance from this A transistor will be R over N, and equivalent resistance from this 100 times wider one will be just 100 R, and we wanted to have this R. So we have 1 over N equal to 1 minus 100. This is quite close to 1, so 99 over 100. So the answer will be n equal to, so 100 divided by 99. This is quite close to 1. So you can understand, if we made this reset transistor wider and wider, then eventually, while keeping the equivalent resistance of this pull down network as close to that of our unit 1 R, but still we can have almost unit transistor here. So then the input capacitance of our transistor, our input capacitance of seen from our input node A can be reduced as just 3 times of our unit capacitance. So 3C can be obtained. What is the 3C? The 3C is the input capacitance seen from the input node of our inverters. Wow, that is really tremendous one. So, but how did we get such kind of improvement? This improvement was only obtained at the expense of this reset. So in terms of this reset, what will be the capacitance? It will be almost 102. This is too severe to be borne by this system. So simply speaking, okay, you can slightly tweak these parameters to have a better performance, but not too much. If you just emphasize one side, and there will be always a negative side effect to the other part. So only when your A signal is much critical than the reset signal, you can apply this technique. Another one is skewed gate. Yes, so let's just say that we always try to match the pull up network and pull down network, and we wanted to always try to match propagation delay for falling edge, which is governed by our pull down network, and rising edge, so pull up network is also in a similar way. However, let's suppose that the rising output of the inverter is most critical. So this one is important. We wanted to have a really sharp transition in this part, and we don't care about, for example, this falling up. Okay, so usually what we wanted to have is well balanced system. So reasonable value of rising time and reasonable value of falling time. This is really well balanced system. However, let's suppose that for some special case we are highly interested with only this one, and we are willing to sacrifice, for example, this one. Let's say, then what happens? Then we may downsize the non-critical NMOS transistor. Or what is the benefit of this NMOS, smaller NMOSFET? Of course, if you reduce this NMOSFET, then the relative strength of your pull-down network is weakened, so there is not sufficient driving force to drive your Y output down to 0. So it will take longer time. However, in this case, with this small device, it does contribute less capacitance to our output. So therefore, it is also beneficial to get further increase of this lighting edge. So now it is also, you may understand, wow, sounds great, but if we consider this falling edge, then you know that now we have much weaker transistor, and relative strength or relative width of our transistor P MOSFET is 4 times wider. So since it is 4 times wider, so it will take quite a long time for our MOSFET pull down this huge capacitance, relatively huge, greater capacitance seen from this Y node. So it is also at the expense of a non-critical path, okay, non-critical transition. So always there is one pros and there is one cons. Okay, so now let's go to our final slide, I think. Then now let's keep this discussion a little bit further. So okay, so then here we have a unit and MOSFET. Then up to now, what was your choice for this P MOSFET size? So we typically take this number 2 under the assumption that, okay, mobility of our P MOSFET is about 2 or 3 times lower than that of N MOSFET. So therefore, we must match it. So why we have to match it? Because once we match these strengths of our pull up and pull down, then what we can say is there is a common capacitor, and if we keep the same R values, okay, this is R, then pull up time will be given by this RC product. And if we have also same pull down network resistance R, then this discharging time will be the same. So our usual way of thinking is we wanted to match the propagation delay for falling edge and rising edge. That is quite a reasonable approximation or consideration. But now, instead of that, now inspired by wow, we can by just play with the relative ratio between P MOSFET and N MOSFET. Sometimes we can intentionally increase and decrease certain edge. So what is the best PN ratio? In this slide, we first assume that, okay, we can individually controlling falling and rising transition time, then by taking their average PD, PDR, PDR, let's say that this is a propagation delay, average propagation delay. How about the minimizing this one? So although it looks like this, but anyway it is much better than this one. So that is our way. I mean that in this lower graph, you can see that quite a long propagation delay and quite a long propagation delay. Yes, and they are balanced, but their average transition is quite long. But you know that here we have a highly unbalanced one. However, anyway, when you make the average of our transition, then it is much shorter than this lower one. So maybe is it better, or anyway, let's say that this is the better conditions for our PN ratio determination. Let's assume this is our assumption. Then here in this textbook we play a quite interesting manipulation. So now let's say that we have the given width 1 and we wanted to change this p values. P value, the nominal value is 2, but how about, for example, 3? Then is it good for average transition time, or say 1.5? Is it good? So let's try to do some evaluation. So our assumption is that, okay, P MOSFET has mu times higher resistance than our P MOSFET. For example, let's say that mu equal to 2. Then our obvious choice is, okay, P equal to 2. Why? If we say so, then N MOSFET will give us resistance R, and also P MOSFET will give us resistance of R over P. Oh, sorry about that. Sorry about that. So since in the case of a P MOSFET, so basically it has larger resistance due to the mobility degradation. However, it is compensated by our wider width P. So if we say mu equal to P, then this factor goes to 1, and so N MOSFET and P MOSFET are balanced. That was our actually our previous approach. Then now let's try to do something. So this is propagation delay. Then propagation delay for falling edge. So in this case, falling edge is given by the R over our transistor, and times there is a certain C. Who decided this C? Actually, sum of this 1 and P determines the C. So can you understand? This is corresponding to the capacitance. And where is the effect of R? Yes, we have R. So simply speaking, we have to do this way. PDF is in its real value. More explicit way, we have to multiply R times the capacitance, and capacitance is given by P plus 1C, because 1 is originated from our N MOSFET and P is originated from our P MOSFET. Their own diffusion capacitances are shown here. So we just understood this RC. That's the reason why we have written in this way, P times P plus 1. And now let's go to the other part. So Lightning edge. In this case, still we have the same capacitance. This is originated from capacitance, so capacitance is the same. Then we must consider the resistance. Resistance is not just 1, but it is given by the ratio between mu and p. Yes, this is given here. And we can just make certain average. So simply the arithmetic average, then you get this value. So now when your mu value is given, like 2 or 3, then you can find out the best condition for your p value. What is the value for your p value? That you can do it. So as a result of this consideration, you find this condition. This is the best condition for considering or selecting your p value, not just the resistance ratio, but square root of it is the best ratio for it. So please note that this is our conventional way to select the P MOSFET with relative to the N MOSFET. Then when you just consider this P equal to mu condition, then what will happen? So since mu equal to P, so this one just becomes 1, also this one becomes 2, and this one has a half, so everything just cancelled out. We have just P plus 1 or mu plus 1 in this example. Okay, so that is the conventional case. And here, in order to minimize this TPD, so we have introduced a seemingly quite strange condition. And if we introduce this condition into it, then now it becomes just 1 plus root mu, and this one becomes also 1 plus root mu. So our answer becomes this one. This one is the propagation delay if we take this scenario. So here we have one simple graph just showing that propagation delay, and y-axis is propagation delay and y-axis is mu value. Then you can see that this one is corresponding to mu plus 1 graphs, and this red color graph is corresponding to the one we can achieve with minimizing condition. So of course, when you have mu equal to 1, then the best way is just taking 1-to-1 ratio, then both cases predict the shortest one. However, if we go to the realistic one, our range is more or less 2 or 3, then you can see that, well, average propagation delay can be slightly reduced by this other approach. So well, you can slightly get better average transition propagation delay. Well, although this is the last slide of our today's presentation, but actually the main deliverable in this slide is not this one. Actually, this delivers you a long signal. Well, now you can get a little bit improved signal, but please try to estimate the real gain. How much? So if you have mu equal to 2, it simply means that you have previously p equal to 2. But now, following your new approach, then now your p values is about 1.4. You have significantly reduced p MOSFET. And the next question is, how about the difference? Can you find this difference? Actually, this difference is not that high. This is really marginal, and according to the textbook, its improvement is just 3%. But 3% sometimes can be a big deal. And also, since our P MOSFET has much smaller width, then it is also beneficial in terms of area. Wow, good. Then why don't you just try to this approach? But in reality, this is not the choice, because it will introduce once again certain imbalance between our propagation delay. So this one will just give you relative length 1, but if you have this 1.42, then it gives you 1.4. So your rising transition is 40% longer than your falling transition. So it means that your, how can I say, your propagation, then if that is not that much balanced, then after some sequence of logic gates, then nobody knows what will happen for your signals. You cannot estimate everything is well balanced or not. So that will introduce severe problems to your system. So that's the reason why, instead of just merely reducing the sum of our propagation delay, but we wanted to have minimized them all together while keeping them in a balanced way. So in order to set the value of this transistor sizing, not only the propagation delay, but we have to consider area, of course, and power, and also reliability should be considered. Unfortunately, in this course, due to time limitation, we have not much thought about reliability problem. But reliability problem is also very important one, because once you sell your chip, then are you free from any kind of obligation for customer? Actually not. For example, if you sell a chip to some guy, and after just 1 year or 2 years later, all of your chips shows some tendency to fail, then your chip companies will complain about you. So I made a design according to your technology, and if I make it with another fab, then it shows some reliable behavior even after 1 year, 2 years, 3 years. But why your company makes such kind of unreliable device? Then that will make a critical impact on your business. So reliability is also very important, not only for transistor guys, fab guys, also for designers. One design house with the same foundry service makes quite good design which is sustained for a long time, and another design house generates a lot of problematic designs which seems to be working. However, after a short time later, something unexpected can happen if you don't care about the reliability. So reliability means that after not a fresh device, but if you have used it for a long time, then what will happen? That is the main topic of reliability. And this reliability is in many ways related with the defects, physical defects inside where? Inside your oxide layer in our modern transistors. You know, here we have a gate and oxide and source and drain, and everything which is quite difficult to solve always occurs in this oxide layer. So reliability is critically related with their oxide problem. Okay, so I think that today's lecture is the part 1 on the circuit family part. So chapter 9.2, section 9.2, and in the next lecture we will consider another circuit families which does not use the P MOSFET, try to use only M MOSFET in order to get, in most cases, higher speed. Sometimes you can sacrifice, for some special case, you can sacrifice the power consumption, then you can boost up your speed consideration. But this is not applicable to every case. So we have to use it only cases for it is really beneficial, significantly beneficial. So next lecture we will consider it. And my advertisement is, okay, this is lecture 22, and we will spend one more lecture hour for combination circuit design, and we will spend lecture 24 for our sequential circuit description. After that, our final lecture, lecture 25, will be devoted to some discussion on SRAM. SRAM is quite an important memory device in our logic system, so we will talk about how can we really implement SRAM with CMOS technology. Okay, although for example DRAM, its fabrication procedure is much different from conventional logic gate, so usually DRAM cannot be integrated into your CPU, AP or something. However, in the case of SRAM, it is really follows the fabrication procedure of a conventional logic gate, so it can be implemented inside your chip. So, and also it has many different properties, but that will be covered in our last lecture, lecture 25. Okay, this is the end of my presentation. And do you have any question on today's lecture contents? Okay, if not, then I want to wrap up today's lecture. Thank you.